This is one of the most highly tuned machines in the world. It was born for one reason and one reason only: to race. And win.
In just a handful of seconds, an F1 car accelerates to the kinds of speeds at which a jet aircraft takes off. In fact, they're so fast that the engineers have to work hard to stop them taking off. And that kind of high performance calls for titanium, carbon fibre, all those other exotic modern materials. But it also requires some surprising engineering connections.
A revolution in artillery. A new design for a jet engine.
Any second now, it's about to snap.
Oh, yeah, there it goes, there, look, look. That's ruined.
An ancient boat. Protective armour. And a sword.
Chaps, broke my sword.
An F1 car has just one purpose in life: to go as fast as possible around a circuit for roughly 200 miles on a Sunday. Everything you see is engineered to improve performance, to shave weight and milliseconds off a lap time. The materials, the engine, the shape.
Famously, their sophisticated aerodynamics keep it pinned to the road so well that it could drive through the Monte Carlo tunnel upside down. Well, theoretically. But the thing is, there's nothing superfluous on these machines. Nothing that isn't about making it faster, pinning it to the road, or stop quickly. That's why there's no room for luggage or a map.
The result? A thoroughbred machine that weighs about half as much as a small runabout. But it's still a car. It does the same things as ordinary cars, just a lot faster, a lot more expensively, and without the indicators. You might think that F1 cars would be built around monstrous engines, but the engines are smaller than those in many family cars, just 2.4 litres. The secret is precision, not brute force. And that precision is audible. It's the distinctive sound of components moving at speeds that would destroy an ordinary engine.
The beating heart of any car with an internal combustion engine, be it a family hack or an F1 car, is this. This is the piston in the cylinder. We've cut the cylinder away here so you can see what's happening. And it starts with an explosion from fuel up here. That's the internal combustion bit of an internal combustion engine. Those expanding gases push the piston down inside the cylinder. That does two things by rotating the shaft at the bottom. Firstly, it sends another piston up to the top ready for its explosion to continue the process. And that rotating shaft ultimately is what drives the car's wheels. You can increase the amount of power by increasing the number of these pistons in their cylinders and by increasing the RPM, the number of times a minute that the piston goes up and down and turns that shaft.
While F1 engines might share the same basic design as an ordinary engine, a piston going up and down inside a cylinder, the engine in your road car would literally explode if it reached even half the revs that an F1 car is capable of. The heat and pressure would be too much. This is how F1 designers engineer the solution. They get more out of each explosion up here, thanks to a huge leap forwards in artillery development. Internal combustion engines are like cannons. They both use an explosion at one end to drive something along a tube. Same process, very different effect. And to get the most out of your bang, you must reduce something called windage. Not good for a cannon or a finely tuned engine. To find out why, I've come to a typically sophisticated and glamorous F1 location with artillery expert Nick Hall.
So this then is the point at which F1 technology and military artillery history come together. What do we need to make it good?
It is important to have the fit between the projectile the cylinder. And in the early history of artillery, because you couldn't bore a cylinder very accurately and you couldn't make an absolutely reliably spherical cannonball, there had to be a gap so that the cannonball wouldn't jam, and so you lost power through that gap.
A windage gap was a safety feature to ensure that a cannonball didn't get stuck in the barrel. But there was a price to pay.
So this is the gap between the projectile, the cannonball, or in this case, the piston, and the cannon itself, the gap around the outside.
Yeah, that is the windage.
Well, I've got two projectiles here, two pistons. Now, we've got one is smaller than the other. One is a little bit smaller, there's a bit of a gap. Do you reckon that's sufficient difference between the size on the projectiles to make a difference in how they perform in the cannon?
Yes, I do, because that gap expressed all the way around is allowing a lot of pressure to escape.
So just that tiny difference will make a difference in what we see when they're fired out the cannon?
Yeah.
So, first, the smaller of the two, with the slight gap. This should affect the performance of the cannon slightly, but will make it safer.
I've got the bigger one.
Which is probably just as well, as this is the first cannon I've built.
OK, well, let's load it up. So, just drop that in.
Yeah.
It's in, I'd say. Now, let's charge the cannon.
My finely machined cannon stores air up to a pressure of 5 bar, or 72 pounds per square inch, which, when released, will hopefully propel the projectile down our makeshift range.
Right, our cannon is charged.
Yeah?
I'll go on 0.
So I can run.
3, 2, 1, go. OK, if we're ready, in. 3, I've never fired a cannon. You fired lots.
Yeah.
I'll just do it quickly. 3, 2, 1.
Released by means of a high-tech lever and rope assembly, the pressure forces the piston along the cylinder and into the air.
Well, it works, isn't it?
That's very good, isn't it?
Well, that's it. That's the smaller projectile. So what we must now do is go and mark
smoke.
the spot with my industrial golf flag. Look at it.
A very respectable 48 metres on our first attempt.
Right. Well, this isn't an exercise in demonstrating the effectiveness of my air cannon, but come on, it's pretty good.
It's not bad at all,
So that's
is
the
it?
slightly undersized projectile, piston, with a slight gap in it around the cylinder bore, which we call windage. This one is now a snugger fit. So if this were too big and you had to squeeze it in, it would waste energy in overcoming the friction to shove it out the barrel.
Yes, but we've got very fine machining here, haven't we?
Only the best. OK, so let's put... Now, that is a closer fit.
In fact, such a close fit, it may need just a little persuading. With our snugly fitting piston finally in place, the air pressure is built up to exactly the same 5 bar level as the previous attempt. There is no windage gap in this one, no safety gap on my homemade high-pressure cannon.
Right, the cannon is charged. We've persuaded the projectile into the barrel. I'm going to stand a bit further away now because I'm suddenly a bit more nervous.
No windage on this one.
No. If I go on 3, 2, 1,
Yeah.
go.
Yeah.
OK, if we're ready, 3, 2, 1. Whoa!
Pretty convincing.
Yeah, it even sounded more dramatic at this end, and that's clearly gone substantially further because of that tiny, tiny bit less of a gap around it.
That's right.
So exactly the same force fired it much further, and all because of a better fit.
3.
Well, we know it went further than the previous attempt at 48 metres, but by how much?
11, 12. So this got an extra 12 metres.
From 48. So
25% increased range from just that tiny, tiny extra bit that closed the gap.
Yeah. So you're not wasting that pressure and gaining range by better fit.
But I really could not see the difference between the two. Barely. You could just about feel it with your fingers.
Not much more than
this one is a
thumbnail thickness.
25% more efficient, effectively. It's the same charge, same power.
Yeah.
So that's more efficient by cutting down on that windage.
Precision machining meant gunners didn't have to allow for windage, all thanks to one John Wilkinson, known in his day as Iron Mad Wilkinson. In the late 18th century, he developed the cannon lathe to machine cannon barrels very accurately. And Wilkinson also realised his cannon lathe could make more powerful steam engines with precisely bored cylinders. The same principle makes F1 cars faster down the straights.
So just that tiny difference, that tiny increase in size, made all the difference in this as a projectile out of my cannon. And if we think if that were working as a piston in an engine, firing thousands of times a minute, it would make all the difference there as well.
F1 engines are so finely tuned and the fit between the piston and cylinder is so tight that you can't even start the engine when cold without damaging it, as Mike Gascoigne, an F1 technical director, explains.
So this engine right now is stone cold.
Yep.
And therefore, inside those cylinders, the pistons are actually
Too tight. If you
well,
start
pretty much
this,
attached.
yeah, if you start this now, it won't break, but it will wear and reduce its efficiency. So we have to plug in oil and water heaters, and we actually have them on timers overnight, such that they come on about 3 hours before we get in, such that the engines are sitting there at operating temperature, and then we can turn them over.
So when you talk about tolerances, which is how closely things are engineered and made in terms of size, in this instance, then, they're so tight that until they're at the right temperature...
Yeah, they're hot home. They're actually fitted together when they're hot. So at temperature they're going to be operating at, that's how they fit them together.
And this is why these things end up sitting there looking there like they're on life support.
Yep.
With water being fed to them and warmed oil to get them to operating temperature.
Exactly.
An F1 car revs to 18,000 RPM,